Okay, so this is the pole scale equation. So I will subtract on that the macro scale, the average equation divided by epsilon beta, assuming that locally the porosity is not varying too much. Okay, so if I do that, I will essentially subtract something like that, which is this equation. I just rewrite that equation. So if I subtract that, I will get the governing equation here for the concentration deviation with the important terms are those terms. Not easy to do that on a oral. Plus terms which are integrals, integral terms. This is the governing equation, so I will have essentially term variation of the deviation concentration, a source term here that depends on the fluctuation of velocity and the gradient of the average concentration, something that will advect the term that will affect the deviation concentration, and then diffusion that, and then additional terms which are of very slow varying properties. So the most important term on these equations are those. Now, there is also a boundary condition. Can I get rid of this at this time? You are okay with that? So I have the macro scale equation, which reads something like this stuff. I have the micro scale, macro, micro, and I have a boundary condition, which essentially gives the following. So now, two things. Those coupled equations are all time dependent. What is the characteristic time scale of this equation? This is something related to the diffusion coefficient d beta. So the characteristic time scales here is something which depends on the small scale and which depends on the micro scale, the free diffusion coefficient. What is the time scale here? Well, that's a little bit complicated. Of course, if I initially put just a spot of concentration, then the time scale and the length scale associated to C beta will be small. But this is not the kind of process I am interested in. I'm interested in, for instance, the behavior of a pollutant in a reservoir or in an aquifer. So I'm interested by scales which are much larger than the small L. So after a while, it's not that simple. It's something straightforward. The while here works because I'm working with a diffusion adduction equation, which is non-degenerate. So there is a. But it turns out that if you have diffusion adduction equation, there will be some smoothing, and in the end, this will have characteristic length scale which are much larger than L. So let us assume that. I should put here LC, but most of the time for simplification, we will assume that LC is actually the large scale of the system. And so the characteristic time scale will be something like that. So far, I do not know that. If D star would be 3 order of magnitude, then I could not. So I'm stuck at this point because I don't have that particular characteristic time scale. But it turns out that most of the time, and then I have to verify that, at the end of the process, at the end of that scaling, I get something which is 1 order of magnitude. Maybe there are different cases, so I have to check that. But in most of the time, I can assume that the time scales are organized like that. So in that case, it's like when you solve an ODE system, if you have eigenvalues which are very, very different, the small eigenvalues you just put 0 in your system, for instance. So I can solve a steady state equation here. It's not a steady state. It is still time dependent, but the time dependencies comes only from that. So in this coupling, I have the time evolution at the macro scale of the average concentration, and then I have a local steady state coupling that will essentially relate my deviation to the gradient of the concentration. Is that okay with you? That's important, and I will show later for heat transfer that this is not always the case. So I have to verify that this is correct for my application. But if I do, for instance, diffusion in a double porosity system, like in many catalytic beds, then there will be 2 time scales, one for the macro scale porosity and another one for the micro scale porosity in the beads. And there are many, many cases for which the time scale, there is a 2 order of magnitudes difference between those two. And so if your packet bed is not big enough, there will be problems. So it's not always the case.
If not, if the time scale was not separated, would you end up with a sort of time convolution term?
That's in the next slide. So I will be back to that later. Okay, so now I have all that stuff done, and I can introduce a closure of the problem, and which takes into the advantage of the fact that I have a linear equation here. So the closure here is almost the same that for the simple problem, and this equation which essentially leads to so the additional terms are discarded here, the integral terms are discarded, they don't play a major role. So I have a governing equation for this mapping vector with a source term that depends on the fluctuation of velocity and transport of B, and the boundary condition here with a source term that depends on the geometry of the system. Okay, this traditional standard condition, and plus I just put here periodicity condition, and remember that of course it must be discussed depending on the kind of material you are interested in. So that's the closure, and if you solve that, then you will be able to transform your average equation into, which is called a dispersion equation, in which I have this accumulation term we already discussed. I have this macro scale advection, where I could put epsilon u here, the intrinsic velocity, and this here I have effective diffusion, mathematically speaking, and this effective diffusion tensor actually is not purely diffusive. There is a diffusive part, which is the original diffusion coefficient corrected by a tortuosity term that depends on this dyadic n dot n tensorially multiplied by b. And I have this additional term here that depends on the fluctuation. So this is the structure, mathematical structure of the effective dispersion term here. I would like just to emphasize 2 things here. The macro scale flux is that part. So in the macro scale flux, there is a restriction due to the fact that we are working with a pulse medium, and there is also a restriction because our pulse medium is tortuous. That's very important. Many people, and often in many books, are things are written, you don't know what are the definitions. So I recommend to look at the way the equations are written to be sure that often people, they just write, they get rid of epsilon because they assume it's homogeneous, but you can do that, of course, but this part is not the macroscale flux. You have a, here if I have a free layer, the microscale flux is just a fixed law in that particular case, and here the macroscale flux is minus epsilon times the. Do not forget that, because if you have a 10% velocity, for instance, you make 1 order of magnitude error, which is of course important. And just before lunch, I would like to take advantage of that to show just some results which are classical. So this, in the diffusion case, this effective diffusion part versus the original molecular diffusion coefficient versus porosity, it looks like something like that. So it's not the straight line here. So there are some tortuosity effects, but tortuosity effects in this particular case are not very important. Often, let me say a word about tortuosity. The word tortuosity has been used in many